Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smartyurl.it/Jedi. My advice on how to pass actuarial exams is at smartyurl.it/pass. This video channel is at smartyurl.it/pass actuarial exams. Here you have information about online seminars and study manuals for exams PFM, IFM, and LTAM that I offer. I direct the actuarial program at Illinois State University. You can find information about it at smartyurl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smartyurl.it/help-ISU actuary. Here's a problem for today for exam P on probability. Compute the expected value of the random number of coin tosses until a run of k successive heads occurs when the tosses are independent and each lands on heads with probability 1/2. And here's the solution. So let x be the random number of tosses till k successive heads occur. Note that if x is equal to n, then n is greater than or equal to k, and the last k tosses were heads. The one just before those k was not heads, so it was tails, and there were no k consecutive heads on the n minus k minus 1 rolls before that. Therefore, the probability that x is equal to n is 1/2 to the power k, which is heads on last k tosses, probability of that, times 1/2 tails on the toss just before that, and probability that there are no k consecutive heads on the first n minus k minus 1 tosses, which is the probability that x is greater than n minus k minus 1. Okay, well then if we multiply out the two powers of 1/2, that's 1/2 to the power k plus 1 times probability that x is greater than or equal to n minus k. And so it's a form of a recursive formula for the values of this random variable that we just obtained. This is equivalent to the statement that for n greater than or equal to k, the probability that n is greater than or equal to k is equal to 2 to the k plus 1 times probability that x is n. Just multiply both sides of the displayed equation by 2 to the k plus 1, and you get exactly this. We also have x is greater than or equal to k with probability 1, which means that we can use the Darth Vader rule to find the expected value, because x is definitely non-negative with probability 1. And the probability that x is equal to k is exactly equal to 1/2 to the k, which is 1/2 to the k. And then the probability that x is equal to k plus 1 is 1/2 tails on the first toss, that's the probability of it, times 1/2 to the k, which is heads on second, third, and so on until k plus first toss. And that's 1/2 to the k plus 1. Then the probability that x is equal to k plus 1 is 1. That's the probability of getting anything at all on the first toss times 1/2, probability of tails on the second toss, times 1/2 to the k, which is probability of having heads on third, fourth, and so on up to k plus second tosses, and that's equal to 1/2 to the k plus 1. And the same way, as long as 1 is less than or equal to r less than or equal to k, the probability that x is equal to k plus r is 1 times 1 times 1, r minus 1 times, that's the probability of getting anything at all in the first r minus 1 tosses, times 1/2 tails on the rth toss, times probability of heads on the r plus first through r plus kth toss, which is 1/2 to the k, and that's equal to 1/2 to the k plus 1. The above gives us probabilities that x attains the values of 1, 2, 3, and so on up to k, k plus 1, so on up to 2k, and beyond those values we can use the recursive formula we derived in the first step. And therefore, the expected value of x, which is by the Darth Vader rule applied to this discrete random variable equal to the sum from n equal to 1 to plus infinity of the probability that x is greater than or equal to n, which is the sum from n equal 1 to k minus 1 of the probability that x is greater than or equal to n, and then starting from n equal to k to plus infinity, probability that x is greater than or equal to n. those first terms from n equal 1 to k minus 1, the property that x is greater than or equal to n, that's equal to 1 because you can't have k consecutive results the same without having at least k tosses. So that's sum from n equal 1 to k minus 1 of 1 plus the probability, sum of probabilities from n equal to k to plus infinity of the probability that x is greater than or equal to n. So that's equal to k minus 1, the first sum here, plus, and then we rearrange this summation here. We want to replace the n by n minus k. Well, then this expression becomes the sum from n equal to 2k to plus infinity of the properties of x greater than or equal to n minus k, because when this n is equal to 2k, then 2k minus k is equal to k, and here when n is equal to k, this is the property that x is greater than or equal to k. So this is just like a change of variable. N is replaced by n minus k, and then we have to start counting from 2k. And then this is again k minus 1, the first term, and the second expression is equal to this expression based on the recursive formula we proved. So this is the sum from n equal to 2k to plus infinity of 2 to the k plus 1 times the property that x is equal to n. Okay, well, we factor out 2 to the k plus 1 from this, and this becomes k minus 1 plus 2 to the k plus 1 times sum from n equal to 2k to plus infinity of the property is x is equal to n. Okay, that's k minus 1 plus 2 to the k plus 1 times 1 minus the probabilities that x is equal to n from 0 to n minus 2k minus 1, really, because we take out 1 minus everything that is before where we start here, basically. This becomes 1, this is 1 minus the probability of values that happen before 2k, which is the first one that we consider here. So this is, again, 1 minus the sum from n equal to 0 to n equal to k minus 1 of the property that x is equal to n, which is all 0 because you can't have x equal to anything smaller than k for k consecutive values that are the same. And then this is the minus the sum from n equal to k to n equal to 2k minus 1, because we started 2k here, so the last possible value is n is equal to 2k minus 1 of the properties that x is equal to n. Okay. And then that's equal to k minus 1 plus 2 to the k plus 1. And what is, well, first of all, 1 minus, but what is this probability? Well, we figured it out before. That's just 1 over 2k, 1 over 2k plus 1, so on. And the last one is 1 over 2k plus 1. And so all these actually, after the 1 over 2k, all these repeat. And then how many of them are there? Well, it's this one and then k minus 1 of these 1 over 2 to the k plus 1. So this becomes k minus 1 plus 2 to the k plus 1 times 1 minus 1 over 2k minus k minus 1 over 2 to the k plus 1. Okay. Then all we need to do is just calculate all this out. So multiply 2 to the k plus 1 by these expressions becomes 2 to the k plus 1 minus 2 minus k minus 1, so minus k plus 1. But really minus k minus 1 and plus k plus minus 1, that cancels out. So what do we have left? We have left 2 to k plus 1 minus 2. And that's answer C. Please remember this is copyrighted material. I posted this problem as an exercise online in PDF form before in 2006. All rights reserved. Reproduction in whole or in part without express written permission from the author is strictly prohibited. Good luck in your studies and good luck on the test.